I hope all of you saw the email this morning. An announcement. Question 5 from the homework has been removed. This was the question where you had to implement an SVM and basically come up with a law of nature. It turns out when you deal with astronomical numbers, there are numerical issues which make everything really painful. So question 5 is, just to repeat, question 5 has been cancelled. This is the question about SVMs or implementing the SVM. But if you've already written code for implementing an SVM, it's not like this effort has been wasted, because it will do you a lot of good in the next homework, where you'll again implement an SVM, and this time it will be for data that's numerically better behaved, let's say, and you'll do a lot of similar things. So any effort that you've spent into this would not be all wasted. Okay? Any questions?
I have a question about homework.
Yes?
2.2, we're asked to train a perceptron for one cycle using 0 as initial weights and a threshold of 3 and 1.
That's the bias.
Threshold is the initial bias?
It's the initial bias.
Right, and we're not doing like a margin thing?
No, there's no margin in that. Yes, that was the same question that you asked. There's no margin. It's initial value of B is 3. That will decide basically whether or not you update.
Can you mention what it is about the data that makes it poorly behave numerically?
Two things. One, in the case when you do not take the log, these numbers are huge. And a lot of people had numeric overflows. In the case where you do take the log, I'm not sure what's going on. It seems I have to actually play with the data and do some data archaeology to find what's going on. I have no clue, because when I use a standard SVM library, it works perfectly. Whereas in an implementation of stochastic gradient descent, things get messed up. So it's possible that all of us are making the same mistake, or there's something funny going on with the data, and I don't think it's worth breaking your heads over it. Even though I truly believe that if 80 of you look at it at the same time, maybe we'll find something. But I don't want to do that for a homework. But yes, if I do discover something, I'll let you know. Yes?
Could you point us in the direction of a good resource for your question for the decision list?
Right. That's a good question. So I'll tell you the resource, and I'll even tell you where you can find the answer.
That's even better.
It's in a paper. If you read that, it's a paper by Ronald Rivest. It's the same Rivest who came up with RSA. And it deals with learning decision lists. So if you can read the paper and answer it and convince me you understand what's going on, I'm happy. As long as you know what's going on, I'm happy. So if you read the paper and answer it, do mention it in your answer that you read the paper. Was that another question? Yes.
So for SVMs, if we have data that isn't just apparently linearly separable, do we need to know do we need to explicitly know how to transform it to a higher space? Like for instance with the homework, like when you took the log, you saw that it was linear.
So if you do not know what space to transform it to, there are no guarantees. In the margin, in the case of the hard SVM, there are absolutely no guarantees. In the case of the soft SVM, you'll still find a line. But how good it is a meaningless thing. So very often we end up with the case where we hope that we know the right space, and it's a black art, really. Feature selection and such things. And in fact, towards the end of today's lecture, I'll be talking about model selection, in particular something that a lot of you have already been playing with, which is cross-validation. And I just want to go over this process of cross-validation, where anytime you add a new feature and to know whether it's anything good, you do cross-validation. Other questions? Yes?
So for the perceptron update, I have already done it using margin perceptron. Do I have to change it?
Can you change it? It's only 2 steps.
Okay.
Yes.
Is the bias ever changing?
Yes, it is. It's the B. It's a wait. It's a wait, yes. And at this point, I think I should spend a minute trying to get this to work because I can talk for a while, but I've got some props. But if there are other questions about the homework, yes.
So when you say use the weak learner feature, do you mean output as, so if a minus is corresponding to -1 or 0?
-1.
-1, okay.
Yes. And also think about whether it makes a difference.
Sure.
I mean, is it, in terms of, if I think about linear separability, 0 or -1 should not mean anything, right? If it's but in this specific case, use -1. Okay. This is promising. This is the most progress I've had. Okay. Another announcement, if there are no questions about homework, the other announcement is about the intermediate report. It's due on Wednesday, midnight, and there's no extensions for that. Okay. No extensions for that. For the intermediate report, I want to see that you've made some progress in your project. It has to be no more than 2 pages, and you have to tell me what you've done so far in the project, and it can't just be, I know what I'm doing. So it has to be, if you've collected any data, tell me about the data. If you've thought about it, if you have any reasons to believe certain things will work and certain things won't, tell me about it. If you've read any papers, describe them, cite them. If you plan to read any papers, tell me what you're going to read. It should be a report that tells me that you've made some progress. And no more than 2 pages, please. Any questions? Yes?
2 pages double space? Single space?
Be reasonable.
Size 18 font?
Huh?
Size 18 font?
Size, yeah, right. In fact, I was contemplating whether I should actually specify font and double space and such things, but I figured you're grown-ups.
So when we write this final hypothesis in the EDA boost and we use the deep learners, so we don't write them like a linear classifier. Like if it is x greater than theta, so we don't say alpha times x minus theta because it
No, it's not. It's actually the prediction of that classifier.
Exactly.
So it's alpha I times hi, where hi is a function that takes the input to -1 or +1.
Exactly.
Okay? Other questions? And the final announcement is that your midterms are graded. I haven't released the grades on Canvas yet. I'll do that right after class, and I'll also post the canonical solutions right after class, or maybe by this evening. But I will hand out your midterms at the end of this class. And my plan is to spend the last 20 minutes of this lecture basically just going over the midterm. And we'll talk about that in the last 20 minutes. And for the guys who just came in, announcements right here. Question 5 from the homework has been deleted. The homework is due tonight. You get an extra day as always if you want, with the 10% penalty. And the intermediate report is due on Wednesday midnight. You had some questions about Canvas not working. Is it solved? Okay. And at some point I should try to figure out the contrast of this thing. So let me just. Is that better? Okay. Every week the combination of switches changes. So. I think they are. If they are not, I'll do that right after the. Yes.
So I have a question about SVM versus deep learning. So you made a comment in an earlier lecture talking about how SVM was or is the state-of-the-art algorithm or machine learning technique for learning data. And now you hear a lot of new hype about deep learning, especially with neural networks.
Right. So deep learning is answering the following. So deep learning is one of those things which is still evolving. By the way, just an advertisement, there will be a deep learning seminar next semester. Those of you who are still around, I'm planning to conduct a deep learning seminar where we'll be doing an entire semester of deep learning. But more specifically, there are many perspectives on deep learning. One way of thinking about it is it's neural networks all over again. Another way of thinking about it, and I think this seems to be the convergence of the community. Remember, in everything that I've said so far, I assume that the features are given to you. All the bounds, everything, except for bound, SVM, the optimization, everything assumes that you know the features. What if you had to learn the features? You can think of each feature as being the output of a classifier in itself, or a predictor in itself, and exactly the way you guys are doing the homework right now. What if I build a hierarchy of those kinds of features? I have layers and layers of features. Now the final output is no longer a linear function of the input. It's some wild nonlinear function, and I'm not sure what it is. So one way of thinking about deep learning is its representational. And the reason we see a lot of improvements now is because, one, we understand a very, very important thing, which we've been actually seeing in the last few lectures. This is the point of regularization. We understand how to penalize models that are overly expressive. And without regularization, getting deep learning to work would be really hard. And another thing is this infinite amount of data which is unlabeled. And some deep learning algorithms take advantage of this to kind of better situate this nonlinear model in the search space, so that once labeled data comes in, things get passed. So in order to understand the math of deep learning, I would argue that you need to understand the basics of what we're doing. So you can take this machinery and build up on it and read the deep learning papers. But conceptually, the same problems remain. You don't get anything for free. If you learn a wildly complex function, it can fit anything. You need tons of data to make a really complex function work. So those intuitions are still the same. So yes, I really like reading about deep learning and doing deep learning, and I don't want to spend too much time talking about it because it might take us on a path that will take the entire class. Other questions? Let's look at where we were. In the last lecture, we were talking about kernels. And one way of talking about the kernel story is that, again, it's the same thing that we don't know what features. We know that we have this black box, a machine that can take data and find a separator if the data is linearly separable. What if the data is not linearly separable? And one way of thinking about it is to define these polynomials of your examples, polynomials of your example features, and deal with dot products in the higher dimensional space. And the reason dot products in the higher dimensional space work is because of this theorem, or this observation, specifically in the case of support vector machines. The weight vector for SVM is simply a linear combination of inputs, or input times features, input times the label, yi, xi, with some alphas. Alphas are non-negative. Because this property holds, we're able to show that prediction w dot x is equal to the innermost operation in building this prediction is a dot product between something that looks like an input, xi, and another thing that looks like an input, the new data point, x. So we're taking that dot product, and this dot product is just a dot product in the ambient feature space, but we could always replace it, by a dot product in a higher dimensional space by lifting the inputs into a higher dimensional space. And this doesn't give us anything, because I could have just, explicitly computed this higher dimensional representation of the data and compute the dot products. And the only way we can actually gain something in this process is if we are able to compute a dot product in a higher dimensional space without actually explicitly converting this input into the higher dimensional point. So if you are able to compute the dot product in a higher dimensional space using only the lower dimensional representation of the data, then we've gained something computationally. And it turns out for certain kinds of things, certain kinds of functions, this is possible, and these are called kernels. So a kernel is simply that dot product in a higher dimensional space, and the kernel trick is the idea of computing that high dimensional dot product without leaving the current space. So just I'll go over a couple of examples today. We saw this in the last lecture. This is a polynomial kernel where, say, in this case it's quadratic. The feature mapping could be all monomials, or not all, but just xi's and xi squares. So you go from the n-dimensional space to the 2n-dimensional space. And I want to compute a dot product between two points that look like this. It takes time because 2n is more than n, and in general I could be doing some fancy things here. Alternatively, I could just take the dot product of the two vectors in the underlying space. So you get something like squared. And as an exercise, I asked you guys to prove that this term here will be equal to and it should not be terribly hard to think about this, or it's not equal because there will be some constants that show up. It should not be terribly hard because let's do some matching of pops. There will be a constant feature in both cases, the 1, and the square, that square there, also has the 1. If I have an xi square feature there, it will correspond to a dot product xi square, zi square, and that will show up here also. If I have a xi term, it will correspond to xi, zi, that will show up here. So it turns out it's a theorem, and there are some coefficients, but the coefficients don't really matter because they'll get absorbed into the weight vector eventually, or they'll get absorbed into the alphas eventually. Any questions about this? Yes.
I think there might be some cross term, x1 times x2, something like that.
It's entirely possible. Yes, that summation, that vector is not complete. In fact, it should have all pairs. You're right. So that should be an n² dimensional space. Good point. There should be cross terms because in this one. Other questions? So again, just to drive home this point, the kernel trick is the following thing. I want to work with these degree 2 polynomial, but I don't want to compute that feature representation because I don't have the space. And it turns out mathematically it's equivalent to computing something like this in the low dimensional space, only computing low dimensional dot products or some function of the low dimensional objects, and we're done. And the only reason this works is because the final predictor is a linear combination of examples. So in your next homework, I'll ask you to implement, or not implement actually, I'll ask you to write down on paper another question that was removed from this homework, which is the kernel perceptron. It turns out this kernel trick is not the exclusive property of support vector machines. And in fact, this is an important point because very often people believe because SVMs and kernels kind of developed at the same time, roughly by the same people, people believe that SVMs or kernels are only for SVMs. It turns out It's a more general family of more general property, and there is a notion of a kernel perceptron algorithm. So the other question is, okay, so the kernel is a function of two inputs, two instances, an x and a z. Z is just using z to also indicate examples. Can any function suffice? I can write any function. The kernel of x and z is, I don't know, sine of x transpose z, or cosine. Is that a kernel? And the answer is, you need to think about it. It's not necessarily true, because intuitively, at least the way I've defined it so far, a kernel is a function that's a dot product in a higher dimensional space. In other words, there must be some high dimensional space in which this is a dot product. So any arbitrary function cannot be used, because it should satisfy the properties of an inner product. Namely, it should be symmetric, the inner product of something with itself should be positive, it should be 0 only if the inner product of 0 times 0 should be 0, and such things. So, and here's the sort of mind-bending thought. It's possible that this high-dimensional space is not even finite. Effectively, what that means is I take an example, and the blown-up feature space is an infinite dimensional vector, which means clearly I don't have space to actually store it. It's an infinite dimensional vector, but using the kernel trick, I'm able to compute distances in that infinite dimensional space in an efficient way. Now, if that is not mind-blowing, I don't know what is. So, to check if a function k is a kernel, there are many techniques for doing this, and in fact, you probably have seen this in your homework already. You need to show that for any training set, finite training set of x1, x2, and so on till xn, you can construct the Gram matrix, which is k of xi and xj for all ij. That's a square matrix, and it's symmetric. Well, it's a square matrix, and that square matrix needs to be positive semi-definite. Now, positive semi-definite is a property of matrices. If you remember from your linear algebra classes, if you have a matrix A, which is square, it's positive semi-definite if x transpose Ax is greater than or equal to 0 for all x. I don't want you to necessarily go around proving this. Instead, so that's one way of doing it. You can just build the Gram matrix and prove that it's positive semi-definite. Another way of doing that is to decompose your function into smaller parts, and knowing certain axioms about certain functions being kernels, you build it up. And this is roughly the approach that I want you to take in your homework. If you prove that the functions that you have in your homework are positive semi-definite, good job. But even otherwise, it's okay. So some axioms would be a linear dot product without any lifting. If you have a function x, a k of x and z is x transpose z, it's a dot product in some space. In particular, it's a dot product with the identity lifting map. So it's a kernel. Polynomials are kernels which capture dth order interactions. If you believe that there are second order interactions, you need a degree 2 polynomial. If you believe that you have 13th order interactions, you need a degree 13 polynomial. And this is a point that's actually pretty interesting, because sometimes it turns out in some problems, third order interactions are important. How do you know that? Because I'll give you an example. This is a problem of dependency parsing. In dependency parsing, one particular formalism for dependency parsing, people believe with some linguistic intuition that you need to look at three things, combinations of three things, to make a decision. And combinations of three things are third order polynomials. And a cube kernel turns out did the job. So this is another this is another point where I can actually say, in order to know what is the best kernel or the best approach to solve your problem, you can do this in a few ways. One, you know something about your data. You have some domain expertise, and you use this domain expertise to, you know, just decide degree 17 polynomials are what I need. Or you could do something like cross-validation, some sort of model selection. You try out all kernels. Or the third option, which is unfortunately what ends up happening, is you have some learning algorithm implementation lying around, and it can only support certain things. So, you know, you may have lost the ring under the tree, but it's bright right here, so you search right here. So, and you can construct kernels using certain operations. If you have a kernel K and it's multiplied by a constant C that's positive, then the product is a kernel. And I went through this list the other class, and I'm not going to go through the whole thing again. You can do it on your own time. So this is a special kernel, and it's an RBF kernel. It's called a radial basis function kernel, or RBF. And you may see this quite often. You may see this if you're doing natural language processing. You'll probably never see this. If you're doing computer vision, you'll see this very often, or speech and such things. And effectively, this kernel is computing a dot product. Is saying that you take the distance between the 2 points in the lower dimensional space, and e power minus the distance is your distance in some high dimensional space. And there are parameters, you know, there are tuning parameters involved which are less interesting. The more interesting part is, I claim this is a kernel, and I also claim that kernels are dot products in some high dimensional space. Who can tell me what's the high dimensional space in which this is a dot product? Let me give you a hint. It's not finite. To see that, what you need to do is take the Taylor expansion of e power x. When you take the Taylor expansion, you get every possible polynomial. It's the sum of all polynomials. Now, the good thing about the RBF kernel is it's an arbitrarily expressive function, because you can fit a polynomial around anything. The bad thing is that it's arbitrarily expressive, which means because you can fit a polynomial around everything. So the RBF kernel tends to, and this is an empirical observation as well, tends to overfit a bit. But if it works, why not?
But we can find a fee for that.
Yes, so you need...
That's e raised to power minus x squared minus plus root 2, right? And that would be same for, and dot would make addition in the power.
No, this is not fee, this is k.
But we can find a fee for that.
The fee is infinite dimensional.
Fee is exponential.
No.
Yes.
This is a distance there, it's not a dot.
Yes, but we can make it like x squared plus z squared minus 2x transpose z,
Okay.
and then x squared and root 2x we can take, and then we can.
I see. Yeah, that's
what means. That's what the fee is for.
Yeah, but sure, that's one way of doing it.
Yes.
The more interesting way of doing this is the one that actually tells you that this is a arbitrarily complex polynomial, is to take the Taylor. So, just to go over this point once again, you may have seen, was there a question at the back? I saw a hand from that. Did you? Can you speak up?
Can 2 slides can go. The one before this.
Yes. Yeah, everywhere here there should be a transpose. And the general notation that I've tried to maintain across the class is bold for vectors and not bold for scalars. But I can imagine, sitting at the end of the class, it's hard to say whether something is bold or not. So yeah, there should be a transpose everywhere. So you've probably seen this kind of a function in your homework. Not the current one, but I think the previous one, where you had to show that, come up with a transformation of your data such that the circle becomes linearly separable in the transform space. And the answer to that, one answer to that, is this transformation right here. And the way to see that it works is to basically see that this is a circle, in this case it's an ellipse, and once you transform it to this space, the function is linearly separable. So you can find a plane in the space. And the kernel trick is a way to actually not do this transformation and compute the dot product in the lower dimensional space. So we want a transformation that makes the data linearly separable, and we want to do it without going up. So just to give you an example of how these kernels work, and to give an example of a kernel that's not a polynomial, let's go back to our good friends Boolean functions. And here's a set. Let's say you have n booleans as your input, and just as an example, say you have two booleans, x1 and x2, and I'm going to define the lifting map as this function that takes these two booleans to a space of all conjunctions. And all conjunctions would look something like this. You have x1, you have not x1, everything. What this means is that it takes each of these 4 points into large vectors that look like that. Okay, is that clear? Okay, so what we want is to do dot products in this higher dimensional space, because if we have a function that's linear in the bigger space, then we are able to compute a much richer set of functions, Boolean functions. So we want dot products in this higher dimensional space, and we want to do it without leaving the lower dimensional space. That's the game we want to play. And you might say that there's no reason to not do this, because there are only 4. I can just, each of them maps to 1. But if you have n, then suddenly you have 3 power n dimensional vectors. So you can't store them. So there's no hope in storing the higher dimensional representation. So in general, you want to find the dot products of this 3 power n dimensional space of all monomials. And I'm going to claim that the following function is a kernel. Is the kernel that actually computes this dot product. K of x and z are 2-bit vectors, is the following. First you go over both of these, and at each position check whether the 2 bits are the same or not. Okay, so this is clearly related to the Hamming distance. You find how many positions these 2-bit vectors are the same, and take 2 power that number, and that will give you a dot product. And this is very efficiently computable, because you just need to do 1 pass over the examples. Now, of course, this is just a claim. I could be lying to you, so it needs a proof. I'm not going to prove it in full detail. Instead, let me just give you an example. Let's say you take n equals 3, you have 0, 0, 1, and 0, 1, 1. According to this function, the kernel should be, how many positions is the same? The first bit is the same, and the last bit is the same. So the dot product in the higher dimensional space should be 2 power 2, or 4. And one way to prove that is actually to blow up the features and go to the higher dimensional space and look at the dot products. There is a subtler way of doing this by actually, the dot products are really, these are we only need to count how many positions. Let's say we want to take a dot product of these two vectors. We only need to count how many positions are these two larger vectors the same, right? So only this happens only for the first two. It happens only in this one place, right? And the first one, of course. It happens here because this corresponds to one x1, the fourth position, which is not x1. Is that you? Is that me? Someone's phone ringing. Okay. So now let's think about why is this fourth position the same? It's the same because it corresponds to not x1, and not x1 is the same in both cases, right? These two, just to clarify, the first and the last should have no common monomials. So every monomial that is the same will end up having this the same value in this bit higher dimensional vector, and that's when it happens. That's what contributes to the dot product. And this argument can be formalized, and in the interest of time, I'm not going to formalize it. And I encourage you to go over this. And in particular, I want you to try out the following exercise. Consider the 4-dimensional Boolean space and take two inputs, x and z. Explicitly write down the representation, just so that you convince yourself that you know what I'm talking about. Write down the representation and then compute the dot product. Then look at the number of positions x and z are the same. It's 1, 2, and 3. Only the first three. So the dot product that you compute should be equal to 2 power 3. If it's not, there's something wrong. Another exercise that you should try is to come up with another kernel function. Maybe I'll even ask this in a final exam. Come up with another kernel function where the space of you don't consider all possible conjunctions, but only conjunctions of size 3 or size 2. It's a much smaller space, and think about how you would compute the dot product in that higher dimensional space without actually leaving the lower dimensional space. Any questions? Yes.
If it's not a Boolean,
Sure.
is it still going to be two the same? Like, or
No.
is it okay?
No. This applies only to. This is not just Boolean. This is for this particular kernel. It's a very contrived example. Okay. And in general, if it's not a Boolean, we are basically in the land of polynomials. So if it's not a Boolean, you'll end up using polynomials. And that's a good point. Well, if you're using polynomials or kernels, an excellent software implementation of kernel SVM is called libsvm. It turns out that it's harder to do things like stochastic gradient descent once you go past the linear kernel. The linear kernel is basically no kernel. So if you go past the linear kernel, you can't do stochastic gradient descent, things get a little bit more hairy, and then optimization, we need to get the optimization people into the room and fill up whiteboards with math. It's fun, but there's only one whiteboard. So libsvm is an excellent implementation of the kernel SVM, and it allows you to try out polynomial kernels and also the RBF kernel. And as far as polynomial kernels go, if your inputs are just Boolean, polynomials still work, right? And in fact, think about what a polynomial in degree 2 would mean if your inputs are all Boolean. And that will actually help you answer your own question. What's a polynomial when your x and z, for example, are only Boolean? Other questions? Let me wind up this section. The Kernel trick relies on this observation that effectively we are computing dot products between the weight and a new input, and the weight is a dot product, and the weight is just a sum of inputs, or weighted sum. So you're all you need, the only operation that you need to make all of this work is to compute dot products between inputs. If you're only computing dot products between inputs, we could do it in the ambient space or lift it up. And the kernel trick is a computational trick it's a computational strategy for computing higher dimensional dot products without leaving the lower dimensional space. Now, a couple of caveats. First one, be careful when you use kernels. Because remember that all the bounds that we saw, perceptron bounds and SVM bounds, they all have an R square term. It's R square over gamma square. And R is a function of the underlying dimensionality. When you use a, say, polynomial kernel, or let's say a quadratic kernel, you go from a d-dimensional space to a d-square dimensional space. Now R is a function of d square, it's not a function of d now. So all the bounds are still a function of the lifted up feature space. Even though you are able to compute the dot product efficiently, doesn't mean that the sample complexity is any lower. So this is something that you should be aware of. If you use an arbitrarily complex kernel, you can computationally do the work. But in terms of the number of examples you need to get a good classifier, we're host. That's one caveat. The second caveat with kernels is something I mentioned earlier. Linear kernels allow a lot more optimization strategies. Yeah, you've written SVM for a linear kernel. It's a shame that you can't submit it, but you'll be submitting it in 2 weeks. But writing an SVM for a polynomial kernel is way more work. What that means is that sometimes, because I want to write my own learning algorithm, because I don't want to use vanilla SVM or perceptron or logistic regression, I want to make some little tweak and I need to control the insides of my learning algorithm. And because it's easy to write the linear version of this thing, sometimes it's, in terms of engineering effort, it's easier just to explicitly blow up the features. Especially if it's something like quadratic. And this is done a lot, and this is almost considered to be like the standard, one of the standard strategies, especially in NLP. Okay? Yes?
So how would the RBF kernel be learnable if it has a essentially
The RBF,
infinite?
yeah, that's a good point. The RBF kernel is a funny beast. What it does is it draws circles around positive points and says everything around it is, it can do that. It can draw circles around positive points and say everything around that is positive. And for the RBF kernel to be good, you need to aggressively play with the trade-off parameter and force the kernel to actually make mistakes, force the learner to make mistakes or to get rid of it. So think about the following case. If your data had no noise and you had infinite data, both of which are somewhat ridiculous assumptions, if that is the case, then overfitting is the best thing to do. Right? I mean, if you had all the data and there's no noise, then you should overfit. If you had all the data but there was noise, then what you could do is come up with a strategy to discard examples that are making the model complex, and then you're hoping it's in good shape. Same thing if you have finite but large number of examples. So that strategy for discarding examples is exactly this trade-off between generalization and overfitting. And you need to tune that more aggressively when you go to an RBF kernel. So the final point I want to make with kernels is something I already said. Kernels is not the exclusive property of SVM. The kernel perceptron is, I just want to say it exists. I don't want to say that you should use it. It exists. It's a bit of a pain to implement it because it's more computationally irritating. But the same kind of strategy can be applied to the perceptron algorithm as well. Questions? Yes.
Why can't we just change what the dot product is? Like why?
What do you mean?
So.
In
Oh wait, never mind. Okay, wait.
You take back your
I
question.
take back my question.
Okay, good. That's the best kind of question. Okay, if there are other questions. If there are other questions, I'll take them. Otherwise, we're going to move on to something called a slightly broader discussion on loss minimization. I'll give you 30 seconds. I think 30 seconds are up. So, today I'll probably only talk about the first 2 points here. And I've already spoken about the first one. I just want to regurgitate this because it's an important one. We've already seen an example, an instance of how learning can be framed as loss minimization. And this is a really dominant strategy for learning. With a lot of new algorithms out there for learning, including SVM, logistic regression, and the more fancy ones that we see are in papers these days, like deep learning and all that. The general idea has been, let me write down an objective function that I want to minimize, and then learning is simply optimization, which is another reason why all of you at some point should take an optimization class. There's no reason not to. But I'm getting ahead of myself. Let's just look at the general setup. Setup's always the same. You have inputs which are X, which are, let's say, some things, examples, vectors, whatever. They are drawn from a fixed distribution, P, but the distribution is unknown. And there is a hidden function f that labels examples. So we have a finite, possibly tiny, compared to the total number of examples possible. We have a finite training set, and we have seen how the oracle function acts on those training examples. Our goal is to find a hypothesis H that mimics this function. It's always been the game we're playing. And one way of doing this is to define a loss function, a function L, a loss function that penalizes bad examples. And learning is simply the problem of finding the hypothesis that minimizes loss. I say simply, but if it was that simple, then there wouldn't be a class. So what we want is to minimize expected loss, but we want to minimize expected loss on the true distribution. The true, fixed, and more importantly, unknown distribution. So that's kind of an unpleasant situation. And we do what we always do, which is minimize empirical loss. We minimize the loss on the training set because we believe that the training example represents the distribution. And we just effectively add up the loss on all the training examples and we minimize that. This is the general strategy of loss minimization. But the story is only half done. Because here there is no preference expressed over two hypotheses which may have the same loss. And that's the job of the regularizer. Pretend that that equation is here. I can see it here. I don't know what's going on. So there is a problem here. Yeah, I know. So let's try again. Oh. The equation's there, trust me. And the equation, just in case.
It's just a physical.
Ah, there it is. So there is a problem here because it tends to overfit. And why? Because it's possible to come up with a really complex hypothesis function that perfectly explains your data, except it's basically as complex as your training data. So there's no learning. So we want a way of penalizing more complex hypotheses, and this is the job of the regularizer. The regularizer penalizes complexity. So that gives us the new objective, which is regularized loss minimization or regularized risk minimization. So there are two terms in this objective. There's the regularizer, which penalizes hypotheses for being too complex, and then there is the loss, which penalizes hypotheses for being not good enough predictors. And typically there's a trade-off between these two things. Typically the function that is most complex ends up being the best function, but we don't want that. And the function that's simplest ends up being terrible. So that's the sweet spot that we need to find, and this sweet spot is controlled by this parameter called C. In particular, we've seen one instance of regularization called L2 regularization, and here it's small l. L2 regularization simply says the regularizer for a linear classifier, which is completely defined by a weight vector, is the norm of the weight vector. And this has other interesting properties, namely it forces you to maximize the margin and all those things. Now, that leaves the loss function. There are other regularizers, by the way. Another popular regularizer that's used is L1 regularizer, which is simply the L1 norm. And once you go to the L1 norm, you can't take, it's not differentiable, so things get more complicated. So that's enough about the regularizer. The other interesting part is the loss function. Loss functions should penalize mistakes. And we're minimizing the average loss. So here's a question. Tell me the ideal loss function. What would you like to minimize? What should be the best? The best. If you want to penalize mistakes, so what should the loss function be?
Added on test data.
We don't have the test data. We want to. This whole thing is defined only on the training set. But a part of your answer was right. So can anyone else build up on that? Yes.
Take part of your training data in the same.
No, I want a function which takes, which has this signature. It takes one example and a W, and it has to say whether there's an error or not, or it has to produce a real number. You were almost there, except error on what?
Current decision.
Error on that example. So this W will make it has something to say about this x, right? Because the sign of W dot x can either be positive or negative, and it can either agree or disagree with y. Yes.
What is this xi? Is it a test data or?
It's a training set. We never have the luxury of seeing the test set. Think of the test. If you can see the test set, you can look into the future. And if you can see the test set, you should not, because that will bias your. That basically will give you a bad model. So the ideal loss that we would like to minimize is called the 0-1 loss. And this is simply the error function. The loss function, I've kind of simplified this. Loss of two predictions, y and y prime, is 1 if the error is, if they disagree. It's 0 if there's no error. Would you agree that this is a good thing to minimize? Because this gets larger if there are more errors, so it's a good thing to minimize. And we know how to write errors with linear classifiers. If y times w dot x is negative, then it's an error. So we can just rewrite this a little bit and say y, 0, 1 loss for a linear classifier is 1 if y w dot x is negative, else it's 0. So this is like a good news, bad news situation. The good news is that we are able to write down a loss function. The bad news is it's very hard to minimize it. So this gives us a cottage industry of surrogate losses, where we try to come up with loss functions that look like this function and are well behaved. We've seen one of them, in fact, and that's the hinge loss. So the blue line here is the blue function here is the 0, 1 loss, and typically the loss function is plotted as a function of y times w dot x. And the way you interpret this picture is if y times w dot x is positive, what that means, you're on this side of the curve, on this side of the graph. If it's positive, the w has not made a mistake. So there's no penalty on this side. If it's negative, it's made a mistake and then you get a penalty of 1. That's the 0, 1 loss. And we replace that with a hinge loss, which looks like this. It's, if y times w dot x is more than 1, then there's no penalty because you're on the correct side of the margin. If it's less than 0, you pay a penalty which is as large as the distance of, as large as its distance from 0. So it's linear. So you pay a big penalty if y times w dot x is huge on the negative side. And between 0 and 1, if it's greater than 0, that means you've not made a mistake. But it's less than 1, it means you're within the margin. And SVM likes to push things outside the margin. So there's still some penalty here. So this is called the hinge loss because it looks like a hinge. And this is just one of the loss functions, and actually we've seen everything there is to see about, well, not everything, but we've seen quite a bit about minimizing regularized hinge loss. We've written that's because minimizing L2 regularized hinge loss is equivalent, is identical to the support vector machine. But I said there are other loss functions. Right, so this is the point that I mentioned. There are many variations of this also for support vector machines. And we get an objective like this. We've seen this slide before, I just want to bring it up again. There is a regularization term which says I like simpler hypotheses because simpler hypotheses end up maximizing the margin. There's an empirical loss term, and in this specific case for support vector machines, it's the hinge loss. And the hinge loss just happens to have this functional form. And there's a hyperparameter C that trades off between these two things. And we'll come back to the hyperparameter later. But the interesting bit is you can replace the hinge loss with other loss functions. So there are many loss functions. I've just listed 4 here. And it turns out we've already seen 3 of them. We just didn't know. We've seen the hinge loss. Turns out the perceptron algorithm is minimizing a loss as well. It's called the perceptron loss, which, if you notice, looks a lot like the hinge loss. There's just a 1. There's just this one term here. And that's the reason why the perceptron algorithm looks so much like SVM with stochastic gradient descent. We've seen AdaBoost, and it turns out the AdaBoost is actually minimizing something called the exponential loss, and it looks like that. And maybe next week we'll actually see logistic regression, which also ends up minimizing another loss function. So really, all these learning algorithms come under this big umbrella of risk minimization or loss minimization, empirical risk minimization. Maybe with a regularizer, the perceptron does not have a regularizer. Questions? Yes?
Does the margin perceptron change that loss function at all, or is it still just minimizing?
The margin perceptron changes it slightly, just so slightly. It's not max of 0 comma, it's max of margin comma. Or negative margin, think about So it's just a minor variation. Another important point is I told you that there is no regularizer in the perceptron, and yet, and at least these two for sure have a regularizer. So, and the regularizer is what lets you generalize. It's the thing that prevents overfitting. How do you prevent overfitting with perceptron?
You don't. You just find any valid solution, but you need linearly separable data.
Yeah, but what if I want to inject generalization into perceptron? What's the technique?
Add a regularizer.
You don't. You say I don't want to add a regularizer. Say I don't want to add much. Average perceptron, the only thing left. Yes. So averaging is another way of injecting regularization, and in fact, some people even end up averaging SGD for SVM. I personally have not really found the difference in any reason to add averaging for SVM because generalization is inbuilt into it. But it's such an easy thing to do, might as well do it. So, in the interest of time, I'm going to stop right now because I want to talk about midterms and such things. So, are there any questions? Okay. So, I'll be handing out the midterms at the end of the class. In the 20 minutes that are left, I just want to quickly discuss the questions. And there, if you have any, and just general statistics. It looks like the grad students and undergrads have done roughly similarly. The numbers are not directly comparable, especially the averages, because the numbers of people, number of students is not the same. So I don't know what the point of this. So just for your entertainment.
Are those maxes outliers or are they?
They're outliers.
I know, I was going to say the name's really low if it's evenly distributed.
So it's not necessarily, yeah, sure. It's not evenly distributed. So
Okay, that's what I, more or less what I was getting at.
yeah. Yes, it's not a uniform distribution. The entropy is not high. So my plan is to go over the questions on the whiteboard rather than any slides. So
So you're saying the test is solvable in 20 minutes?
yeah, of course. If you know what you're doing, you have all the answers. And I'm not going to go over every question, obviously. Okay.
So can you turn the front lights on?
Yes. I just turned off a switch called middle. I don't know what that means. I think somebody's playing a big practical joke here. It's engineering. Huh?
Engineering building.
It's an engineering. It's a chemistry building.
That's large.
Yeah. So in any case, let's. And I'm going to go over the entire thing, including the questions that are for grad students only. And general advice, I mean, even though some questions are not marked as for undergrads, especially, not especially for undergrads, I encourage you to see those questions even for the homeworks and the exam. Because it's not like you can't do them, I just want the grad students to do a little bit more work. But you should be able to do any of the questions. So the first question is about decision trees. There's some data set. Oh, why don't I pull up? I can't do both the blackboard and the slide. This is a problem. Do I dare? Yeah. Yeah, I'm not sure. Okay, let's try. So the first question is about learning decision trees, and in general that was an easy question. It was basically just applying the formula for, what do you call it, information gain. So most of you, I don't remember details about who got how many questions, so I'm not going to even make an attempt about that. but I think many of you got that. So okay, so let's that's not a good idea. Okay. This is going to take at least 10 minutes to show up, so let me just leave this on, and if we actually get it to work, we'll see. In any case, so the first question is about entropy and information gain, and the only question that kind of confused a few people is when I asked for entropy of this attribute called price. This was not the label, this was a okay. This was not a label, this was one of the output, this was one of the features, and I suspect most of you could have answered it, but not everyone did because of, I'm not sure what reason.
Maybe you should use this projector next time, class.
I should turn it on for what it's worth. So, right, so let's make this bigger for the people on this end. So you had the first question was finding the entropy of like, and I think that was one fairly simple thing. Second one was finding the entropy of price. That's also somewhat simple. It's just there were not 2 but 3 attributes. So you needed to do summation over all 3 things. And information gain, that's the another bit which was simple enough that I'm not going to spend any time on it. The one interesting question here was the question for grad students only, which is this one. If you have k conjunctions, and what's the smallest size of the tree? And some people confuse this question to think, what's the smallest size of the tree for any input? And I was for what's the smallest input that will give you the smallest tree? But really what I wanted is something like this. If you have x1 and x2 and x3, and let's say there are some negations and so on, the function, the tree will look like this. x1, yes. No, sorry. So it's simply a tree that has k inner nodes, so the size is O of k. And I think some of you tried to double guess and overthink this question, which is a bit of a shame. The second question is about learning linear threshold units, and almost everyone, many of you did fairly well on this. Represent this function as a, I see that the error that was there is still here, so let it be. Represent a function as a linear threshold unit. It's simply a summation over xi, where I equals, what did I say, 1? Let's say 1 to 20 is greater than or equal to 10. Would you prefer to use the perceptron or the Winnow algorithm? Now, this is a bit, so most people said Winnow, and the reason being the number of relevant attributes is very small. A couple of you tried to prove that it's perceptron by looking at the mistake bound and computing the value. It turns out everyone who computed the mistake bound forgot about the margin term, and if you include the margin, it still turns out to be Winnow. So the answer is Winnow. I've given points for anyone who said Winnow and had the word relevant anywhere in that text. VC dimensions of, the VC dimension of linear threshold unit. This is an easy question. It's straight out of the slides, so I'm not going to go over it. The answer is 3. This one should be 3 right here. And we worked this out in the class. It's in the lecture and it's in the video, so I'm going to skip this one off. Nearest neighbors. This is an interesting one. The line goes like this. It goes, you go up. Yeah. Looks like this. No. And once again, so here's a general observation that I made. It turns out that the exam was not difficult at all. It's just that some of you tried to either double guess. There were no trick questions here. And some of you could have done, I believe, based on the mistakes, some of you could have done much better if you had more time. So that's my optimistic outlook here. So, which of the following statements about k nearest neighbors are true? What do you think? Is 1 true? The classification accuracy of k nearest neighbors increases as k increases. It's not true. The k nearest neighbors algorithm does not require an explicit training step. True. The decision boundary of k nearest neighbors is linear. The Euclidean and squared Euclidean distance are equivalent for k nearest neighbors. Some people got confused with this. And the answer is true because when I say equivalent, I mean in terms of the decision. And if you square the distance, the ordering does not change. Now, the next question, you have a learning problem with, I don't know, 10,000 features, but only 10 are relevant. Would you use nearest neighbors or decision trees? What would you use? Decision trees, and why? Because of dimensionality, only relevant features show up in the decision tree. The noise tends to overrun distances when you use nearest neighbors. Any combination of these is okay. Here's a fun example, fun question. You have a training set with only 10 examples. And you're using Euclidean distance, and 9 of them are positive and 1 is negative. Is it possible that no future training examples will ever be negative? Will ever be labeled negative? For irrespective of what your training configuration is. You believe no. Why?
Because you can always find a distance closer, or you can always have us, I think, throw all labels on top of each other.
So, what do you mean?
You just put all the labels on as, like, put plus label on.
They're all distinct points.
You just
Yeah,
have
it's
one
always distinct.
label
Oh,
that's
yeah.
always on top of the negative one. You use the same one again.
So
then it's always
let's say, actually, this question should have had another qualifier, which says, let's say the new future examples are not the same as these 10.
Okay, full circle.
Then what will happen? Yes.
Well, say you have your negative example, and it's in the discrete space, and it's completely surrounded by positive examples.
Okay. But this is in real Euclidean.
Yeah.
You are computing Euclidean distance. There's no assumption of discrete space here.
No matter how close you put them, you can find one that's closer.
Exactly. No matter how you arrange the points, you can always find an epsilon ball around the single negative training example, which will be closer to that point than anything else. So, irrespective of how, if you have even one negative point in your nearest neighbor's data set, there can be future examples that can be negative. Okay, we are doing good progress here. I think we have 5 minutes and we need to do the perceptron part. This was a question that most of you found difficult. And I am not sure why. There are actually probably three things that are different in answering this from the standard, the perceptron mistake bound that we've seen. So, let me just derive this. Okay? The algorithm algorithm M, which is really the margin perceptron, says plus if that's your decision function. The first question asks you, define the notion of a margin. Okay? And the margin is simply, let me, in the interest of time, I should probably just not try to. So you find the score of an example, w dot x minus theta, and every point should be outside. So it looks like this. So this is your, let's say this corresponds to theta, and the margin is everything. If every point is outside it, then that thickness is the margin. So the theta term reduces the score in your margin computation. The second question says, give a single inequality expressing the idea that the ith example is the kth mistake. Prediction is W transpose X minus theta should be positive. It's the sign of W dot X minus theta. And if the sign does not match the true label, then this product will be negative. One common mistake that I saw was in the margin thing, many of you had plus theta here. But that is not right because that does not cover both the positive and the negative sides. Another mistake that some of you made was to have the theta on the other side without the y. And it's roughly the same problem.
But theta is threshold.
Theta is fixed.
Yeah, theta, then it should not be like y. Okay, so this is the margin has like y for.
So this says, okay, it's u. So for all, so the whole statement is for all x comma y in your training set that exists for u, and there, or actually it's the other way around, there exists a u such that blah blah blah. Third part is what's the time? Oh, we are past time. So let's take a vote. How many of you want to stay and finish the third and fourth parts? And how many of you want to take your paper and leave? Good, that's decided. So I'll be posting this on the website soon. And we're going to alphabetize this. I'll probably, so do you want to